Ladies and gentlemen, welcome. This is our fifth seminar of 4ST601, and today we'll solve a lot of regression models. We'll start with linear regression, regression line only, and I will show to you how to solve this line manually. And because you will see that it spent a lot of time, it's not difficult, but it spent a lot of time, I will show to you a lot of examples in Microsoft Excel. So first, make ready your formulas, and after, make ready your English version of Microsoft Excel. So that's all, and we can start. We'll start with the first example. Suppose that we received the data from 6 households about the number of members in the household and their monthly expenditures in thousands Norwegian crowns. So we have here a data set with two variables, independent variable and dependent variable. We would like to explain, yes, the expenditures by number of members in the household. Yes, why? I can draw an image here. Yes, you can imagine a classical scatter plot, for example. Yes, there is a variable y and there is a variable x. Yes, and we have a data set, number of members. Yes, from 1 to 6. So 1 person, 2 persons, 3 persons, 4 persons, 5 persons, 6 persons. Yes, you can do this also in Excel. Yes, and we have datas, expenditures in thousands, yes, Norwegian crowns. So you can imagine the development of this variable like this. Yes, and we are able to explain this data set by some simple function. Yes, Mr. Hellman talked to you about the simple functions of dependence. This one can be, for example, linear. Yes, so we can expect, yes, that if you have more persons in the house, yes, you can expect more expenditures. Yes, more expenditures on this household. So this is our statement, our expectation. So we can try to calculate the correlation coefficient. Yes, correlation coefficient between expenditures and number of members. And we would like to try to interpret the tightness of this dependence. Yes, so I will use another paper. Yes, I will rewrite the data here. Variable x. Yes, 1, 2, 3, 4, 5, 6 members, and variable y, expenditures. Yes, expenditures in thousands Norwegian crowns. 6, 8, 12, 15, 22, 23. Yes, for the calculation of correlation coefficient. Yes, correlation coefficient are between variable x and variable y, yes, is equal to, in the numerator, you can find x, y mean minus x mean times variable y mean, yes, divided by, and there is square root, and 2 parts. There we can find x squared mean minus x mean squared, yes, times, and the same for variable y. So y squared mean minus y mean squared. Okay, so you can see that we need only to calculate some means, yes? So multiplication x, y, yes, x in squares and y in squares, yes. Okay, so multiplication, 1 times 6, 6, 2 times 8 is 16, 3 times 12, 36. I will use calculator 4 times, wait a second, 4 times 15, 60, 5 times 22, 110, and 6 times 23, 138, yes? Squares of variable x, 1, 4, 9, 16, 25, and 36, and variable y, 6 squared, 36, 8 squared, 64, 12 squared, 144, 15 squared, 225, 22 squared, 484, and 23 squared, 529, yes? If you have Excel, yes, you can do this in Excel, it's easy, yes? But I would like to show you one example manually, and all other examples, yes, which we will solve, will be solved in Microsoft Excel only, yes? So I want to show you both ways. Okay, and the means, yes, averages. Okay, so the first one, 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, 3.5, yes, so there will be 3.5, 3.5. Another mean, another average, 6 plus 8 plus 12 plus 15 plus 22 plus 23, 86 divided by 6, 14.33. I will use only 2 decimals, yes? Okay, another mean, 6 plus 16 plus 36 plus 60 plus 110 plus 138 divided by 6, 61. There we don't have any decimal. 1 plus 4 plus 9 plus 16 plus 25 plus 36 divided by 6, 15.17, and finally this one, 36 plus 64 plus 144 plus 225 plus 484 plus 529 divided by 6, 247. 247. Now we have the means, and we are able to use this formula for calculation of correlation coefficients. So in numerator, 61 minus 3.5 times 14.33 divided by, and there is square root, and we have here x squared mean, so 15.17 minus 3.5 squared, yes, times, and there is y squared mean 247 minus 14.33 squared, yes? Okay, so equal sign. Okay, nominator 61 minus 3.5 times 14.33, enter. So nominator 10.845, yes? And this is divided square root, and there we have the first part 15.17 minus 3.5 squared 2.92 multiplication second part 247 minus 14.33 squared, enter. 41.6511. Okay, so denominator 41.6511 times 2.92, enter. Square root from this value. So nominator 10.845, denominator square root from this result 11.028 and other decimal places, yes, equal sign. So 10.845 divided by this result 0.98339, for example, yes. So this is correlation coefficient. This is correlation coefficient R between x and y, between variable x and y. So number of members in the household and monthly expenditures, yes. So you can see that correlation coefficient is positive. We know that correlation coefficient, yes, R x, y is element of range from -1 to +1, yes, and because we are very close to +1, yes, there is very strong positive linear dependence, yes. If you have more persons in the household, you must expect more expenditures, yes? So we calculated the correlation coefficient and we tried to interpret the tightness, yes? It depends, yes? Very strong, there is very strong dependence. We would like to also calculate the parameters of the regression line, yes? That is describing this dependence, yes? This dependence of the monthly expenditures on the number of members in the household. And we would like to interpret, yes, the value of our regression coefficients, yes. Mr. Hellman told to you that classical regression line, yes, y is equal to b0 plus b1x, yes. This is simple regression line, yes. We can write that dependent variable is equal to, this can be called intercept or constant, yes, intercept or constant, yes, constant of the model, yes, intercept, plus b1 can be called slope, yes, slope of this line, yes, times independent dependent variable, which is sometimes called explanatory, yes, explanatory variable. So we would like to calculate, yes, on the basis of our data set, intercept and slope, yes. We have formulas for the calculation, yes, from the data, and these formulas are based on least squares method, yes, least squares method, minimizing the sum of residuals squares, yes, and in formulas you can find that B1, yes, B1 is calculated like nominator xy mean minus x mean times y mean. You already seen this before, yes? We have this here, yeah? Nominator of our correlation coefficient, and in denominator you can find x squared mean minus x mean squared, yes? If you rewrite this in another form, in a nominator you can find Sxy, which is statistic covariance. Yes, this covariance is a special statistic from interval, from range minus infinity plus infinity. Yes, this covariance is element to range minus infinity plus infinity, and you know that our covariance, yes, was plus 845, yes, 845. What it means? Positive, yes, positive covariance, and this means that the line, yes, the line will be increasing, yes, positive nominator, positive covariance means that the line will be increasing. Where is my chart? Here, yes, positive covariance, increasing line, yes, okay, and now denominator. In denominator formulas you can see that in denominator is variance as x squared, variance from variable x, yes, this is variance of variable x, yes, variance of variable x. And variance is non-negative value every time, non-negative value, yes. In our situation, where is our data set? 15.17 minus 3.5 squared, yes. 15.17 minus 3.5 squared. This is variance, and variance must not be negative value, yes? So 15.17 minus 3.5 squared, enter 2.92, yes? So the sign, yes, plus or minus here is dependent only on covariance, because nominator is non-negative every time, yes? Okay, so 10.845 divided by denominator 2.92, enter 3.714, yes. So this is B1, and B1 is the slope of the regression line, yes? This is slope of the regression line calculated on the basis of our data set, yes? And after we have slope, we can calculate intercept. In formulas, you can find B0 equal to y mean minus B1 times x mean. Yes. So again, we need this paper. Yes. Y mean 14.33. 14.33 minus my calculated slope. Yes. Where is my slope? 3.714 times x. You already remember 3.5, yes? 3.5. So this will be intercept of the regression line. 14.33 minus 3.714 times 3.5, and 1.331. Yes, so this is intercept. Yes, this is intercept. Okay, and what else was written here? Calculate the correlation coefficient. Yes, we have calculated parameters of the regression line, describing the dependence of monthly expenditures on the number of members, and interpret the value of the regression coefficient. Okay, so our regression line, yes, y is equal to b0 plus b1 times x. In our situation, expenditures y are equal to b0. B0 1.331 plus 3.714x. This is my regression line, yes, in thousands of Norwegian crowns, yes, in thousands Norwegian crowns, yes. So we have this chart. There is variable x, there is variable y, yes. 0 persons in the household, 1 person, 2 persons, 3 persons, 4 persons, 5 persons, 6 persons in the household, yes. Imagine that there is nobody in the house, yes. Nobody in the household, yes. There will be 0, and expenditures are equal to 1,331 Norwegian crowns, yes. So there is the beginning of the line, and there is increasing line, yes. Nobody, yes, and the value of this function is 1,331 Norwegian crowns, yes. This is some autonomous expenditure, yes, autonomous expenditure which must be paid even if the house is empty, yes. For example, the fee for rubbish, the fee for internet connection, yes, loan, etc. Yes, some autonomous expenditure which must be paid even if the house is absolute empty, and 3,714 Norwegian crowns is average increasing, yes. This is average increasing, with every other person in the household, yes. Another person in the house, and you need more money, you need more by 3,714 Norwegian crowns. Yes, another person in the household, another 3,714 Norwegian crowns, etc., etc. So intercept is autonomous expenditure, which must be paid even if the house is empty. Yes, and this is average increasing with every other person in the house. Yes, so this is interpretation of our coefficients. Yes, both of two coefficients. There was written coefficient, but we have two, intercept and slope. Yes. Using this model, yes, this is our model. Yes, our expectation about the real situation. We would like to calculate average expenditures of the household with 4 members. Yes, you can see there is written, yes, that the household with 4 members, yes, needs 15,000 Norwegian crowns. Yes, 15,000 Norwegian crowns. Yes, so this is reality. And now I will use my model, yes, this one, and I will calculate my expectation. Yes, y is equal to, so autonomous expenditure 1.331 plus 3.714 times 4 members, yes, in the house. Okay, so this y is for 4 members. Yes, y for 4 members. Okay, so my result 1.331 plus 3.714 times 4, 16.187. Yes, so my expectation is this family or this household with 4 members, yes, will need, according to my model, 16,187 Norwegian crowns. Yes. Okay, you can see that there is a difference. Yes, there is difference 1,187 Norwegian crowns between my expectation and reality. Yes, so there is a question. Yes, there is a question if this model is good. Yes, we already calculated correlation coefficient. Yes, we already calculated correlation coefficient, which was very close to 1. So we can expect that this model is good because there is very strong positive correlation. Yes, we have another statistic. Yes, we have another statistic, R squared. Yes, R squared statistic, R squared index of determination or coefficient of determination. Yes, according to we are able to interpret the powerful, yes, of this model. So we will assess the quality of the model using the coefficient of determination, dr square, yes, r squared. For the calculation of r squared, we need to calculate some sum of squares. Yes, sum of squares regression divided by sum of squares total. Maybe I will write for you that there is word regression and there is total. Yes, in your formulas you have written that sum of squares total is equal to sum of squares regression plus sum of squares error Yes, error. Okay, so regression plus error is total, and for this ratio we need to calculate regression and total sum of squares. Okay, so in formulas you will find that sum of squares regression is equal to, there is summation through all e, we need fitted values, ye with hat, yes, calculated values based on our model, fitted values, yes, fitted values by our model, minus y mean, and this must be in squares, yes, okay, so this will be a regression, and now sum of squares total again must be some summation because it's sum of squares, yes, through all e, and there we have empirical values ye, so data set, yes, minus y mean squared, yes. It will be good to use this paper, yes, this paper where we have our data set, and it will be good to fit all values, yes, on the basis of our model, because our model ye with hat, yes, we will calculate our predictions, yes, is equal to 1.331 plus 3.714 times x e, yes, and I must calculate these estimates, yes, I must calculate these expectations, yes, these expectations for all 6 values, yes, 1.331 plus 3.714 times 1, 1.331 plus 3.714 times 2, yes, times 3, times 4, times 5, and 1.331 plus 3.714 times 6. Yes, so I will receive 6 calculated values, yes, on the basis of my model. So I will use calculator, and 1.331 plus 3.714, 5 point, I'm sorry, I will use only 2 decimals, yes, 5.05, 1.331 plus 3.714 times 2, 8.76, 1.331 plus 3.714 times 3, 12.47. We already calculated this value, yes? This will be 16 point something, 1.331 plus 3.714 times 4, 16.19. 1.331 plus 3.714 times 5, 19.90, and finally 1.331 plus 3.714 times 6, 23.62. So these values, yes, which you can see here, these values are fitted values ye with hat. Yes, ye with hat, our calculated values on the base of model. Yes. Okay, and now we need to calculate the squares. Yes, we need to calculate the squares between fitted values and the mean of variable y. and empirical values and mean of variable y. Yes. So now I will use this original paper. Yes, and I need to calculate here y e hat minus y mean. Yes, in squares. Okay, so I have here this column. Yes, so I will use this column and mean 14.333. Yes, so there will be 5.05 minus 14.3333 squared. Yes, and we can continue 8.76 minus 14.33 squared. Yes, and we can continue 12.47 minus 14.33 squared. 16.90 minus 14.33 squared. 19 point, there should be 16.19. Yes, I'm sorry, 16.19, and there is 19.90. Yes, minus 14.33 squared. Yes, and the last one. Yes, you can see, you can check me, 23.62, 23.62 minus 14.33 squared. Yes. Okay, so 6 new values here. Yes, 6 new values. I will use calculator. 5.05 minus 14.33 squared. 86.12. Yes, and we can continue. 8.76 minus 14.33 squared. 31.02. Yes, 12.47 minus 14.33 squared. 3.46. And here I must use correct value. Yes, 16.19. 16.19 minus 14.33 squared. 3.46. 19.90 minus 14.33 squared. 31.02 and 23.62 minus 14.33 squared. 86.30. Okay, and now according to this formula, yes, summation of these squares is regression sum of squares. Yes, so now I will calculate the summation sum of these values. Yes, 86.12 plus 31.02 plus 3.46 plus 3.46 plus 31.02 plus 86.30 241.38. Yes, so this is sum of squares regression. Yes, regression sum of squares. And for the calculation of total sum of squares, you need to calculate here differences, yes, ye, so empirical values, minus y mean, yes, and this must be in squares. Okay, so empirical values, yes, from this column minus mean, so 6 minus 14.33 squared, yes, 8 minus 14.33 squared, 12 minus 14.33 squared, yes. Do you know how I can solve this? Next value 15, yes, minus 14.33 squared. 22 minus 14.33 squared, yes. 23 minus 14.33 squared. Okay, equal sign, etc. And we will calculate another 6 squares, yes, 6 squared values. So 6 minus 14.33 squared, 69.39. 8 minus 14.33 squared, 40.07. 12 minus 14.33 squared, 5.43. 15 minus 14.33 squared, 0.45. 0.45. 22 minus 14.33 squared, 58.83, and the last square, 23 minus 14.33 squared, 75.17. Yes, and according to this formula, yes, if I calculate sum of these squares, I will receive a total sum of squares. So here will be summation, yes, summation of these values. So 69.39 plus 40.07 plus 5.43 plus 0.45 plus 58.83 plus 75.17. 249.34, yes, 249.34. So this is sum of squares total, yes, sum of squares total. Okay, now we have everything. We have everything for the calculation of r squared. But I will show to you one bonus. Yes, this is not necessary. This is not necessary for this example. Yes, to calculate error sum of squares. But I will show this to you, for example, for purposes of some examination, because it's necessary to know how to solve this. Error sum of square is calculated like summation through all e, and there we have squares ye, and fitted values ye with hat, yes, in squares. So, because we have here these fitted values, yes, and here I have empirical values here. Yes, you can see there is variable y, there is y hat. So I can calculate here the differences. Yes, 6 minus 5.05 squared, 8 minus 8.76 squared, 12 minus 12.47 squared, 15 minus 16.19 squared, 22 minus 19.90 squared, and 23 minus 23.62 squared. Yes. Why I show this to you? Just like a bonus, because it's good to know how to solve this. Yes, error sum of squares. So just for our confirmation of results. So wait a second. 6 minus 5.05 squared, 0.90. 8 minus 8.76 squared, 0.58. Yes, 12 minus 12.47 squared, 0.22. 15 minus 16.19 squared, 1.42. 22 minus 19.90 squared, 4.41. And finally, 23 minus 23.62 squared, 0.38. Yes? And now, if you calculate the sum of these values, yes, if you calculate the sum of these values, 0.9 plus 0.58 plus 0.22 plus 1.42 plus 4.41 plus 0.38. Yes, result is 7.91. And this our calculated bonus is sum of squares error. Yes, sum of squares error sum of squares. Yes, we can provide a proof. Yes, because we know that total sum of square is calculated like summation, regression, and error sum of squares. Yes, we have here our squares here. So I will calculate the difference, and I will give you the proof that my error sum of squares is calculated correctly. So the difference, yes, sum of squares error must be equal to sum of squares total minus sum of squares regression. According to our previous results, 249.34 minus 241.38. Yes. Okay, I will use calculator. 249.34 minus 241.38 is equal to 7.91. 7.96, yes, 7.96. You can see I have here a small difference, yes, because of decimal places, but it's all right, yes. I have here the proof that my sum of squares are calculated correctly. And now, final calculation of r squared, yes, this one. So what we need regression, sum of squares, so 241.38, yes, divided by total sum of squares, 249.34, yes. So result will be written here, 241.38 divided by 249.34, 0.9681, 9681. Okay, Mr. Hellman said to you that r squared, yes, r squared is element of range from 0 to 1, and if this r squared is close to 1, yes, the model is good, because the model is able to fit the data very well, yes. Our r squared is 0.9681, so it's very close to 1, yes. And according to this question, assess the quality of the model using the coefficient of determination. According to this coefficient of determination, I can say that this model is good, yes? This model is good because its r squared is close to 1. Okay, another important example. In the table below, there are written the annual costs on the maintenance in thousands Norwegian crowns and the price of the house in millions of Norwegian crowns. So we have here two variables, dependent variable and explanatory variable, and we would like to try to explain, yes, explain or describe the dependence of costs, yes, on the maintenance, on the price of the house, yes, by the regression line. So we will use intercept and the slope of the regression line, and we would like to describe the dependence of costs on the price by this regression function. You know that to calculate parameters of a regression line is easy, but spend a lot of time. So, since now we will use Excel, because in all my seminars you are allowed to use Microsoft Excel, yes? During the midterm tests, during my seminars, but not in the final test, because the final test is written in the lesson hall. So you must know how to solve everything manually, and it's good if you know how to solve it in Excel, because you can save the time, like now, yes? We will save the time. So it's necessary, it's absolutely necessary to use add-in, which you can find on data leaf here in the right side, yes, because I don't have install this add-in here. I must click on file button, yes, so please click on file button, and here on the bottom, yes, you can find options, left bottom part of the screen, options, yes. You will see this window, and there you can find add-ins, yes, again there is a left column, add-ins, you can click on add-ins. And here on the bottom you can manage Excel add-ins, and there is go button with 3 dots. So please click on this Go button with 3 dots, and you will see here Analysis Toolpack. So please select Analysis Toolpack and click on OK. And now you can see I have activated data leaf in Microsoft Excel, and on the right side you can find data analysis. Yes. For your purposes, I copied, yes, these values here to 2 columns. Yes, to 2 columns, variable y and variable x, dependent variable and explanatory variable. Yes, so I will use data analysis toolpack, and if you see this small window, you can scroll down and you can find regression. So please find regression and click on OK button. There you can see again small window which is very intuitive. Yes. It's necessary to select input y range, dependent variable. I said here that you must explain, yes, the costs on the price, yes, by this line. So it's stated, yes, it was said that costs are dependent variable and the price of the house is independent explanatory variable. Yes, so imagine that there is not written y and x. Yes, you must know what is y and x. You must know this. Yes, so I know that this is y, this is x, so I will select these columns. So please select input y range, this column also with label. Yes, input x range is this column also with label. I will select labels because I selected these columns with labels, and that's all. Yes, that's all. You can click on OK, and the least squares method, yes, will provide results for you. So what is the most important for us? Please wait a second. I will delete the cells which are not necessary for us. I will use only 2 decimals here, yes, and also here I will use only 2 decimals. Yes, and this is the output of the regression analysis. So what was written here in A, describe the dependence of costs on the price by the regression line. I used Microsoft Excel. I have here output, yes, and you can find here that I have here coefficients of the regression line. So what can we find here? Coefficients, yes. This intercept is my B0, yes, B0 of the regression line, constant intercept of the regression line, yes, and the second one, x, is the slope of the regression line. So if you want to write the model, yes, the function of the model, you can write, for example, here y, y is equal to minus 161.68 plus 7.58x. Yes, and this is the equation of our regression line. Yes, so this is A. We described the dependence of cost on the price by the regression line. Yes, it's also possible to construct the chart. Yes. In insert leaf. Yes, there is insert leaf. You can find here charts, yes, and one type of chart is scatter, and this scatter plot is very often called XY dot chart. XY dot chart. What's necessary? To have variable X like the first one. Yes, so I moved column Y on the second position, and now if I use this part, yes, charts, there the last one insert scatter, yes, XY or bubble chart, I will use this XY chart, yes, and you can see the dependence. Yes, I will use a little bit larger font. Yes, and you can see positive dependence. Yes, positive dependence of the price of the house on the costs of the maintenance of these house. Yes, variable Y is here. Yes. In Norwegian crowns and millions of Norwegian crowns, the price of the house is here. If the house is larger, yes, the house, large house, yes, has a lot of windows, a lot of flats, a lot of doors, stairs, an elevator, yes, etc. You need a lot of money for the maintenance, yes. If you have small house with one flat, yes, few doors, 3 windows, yes, no elevator, no stairs, yes, you need less money for the maintenance, yes. So there is positive dependence between the price of the house and the cost of the maintenance, because expensive house is probably larger, higher house, yes, so you need much more money for the maintenance. So you can see the dependence, yes, and we calculated the line, yes, the regression line. I will zoom these dots, yes, I will zoom these dots, okay, so it's better visible now, yes, and I can use right button on one of this dot, yes, and that is possible to add trend line, yes, add trend line, and I will select linear, yes, you can see here on the right side linear trend line, and I can display, there you can select display equation on chart, yes, display equation on chart, and I will use higher font, yes, and you can see that this is our function, regression function, but be careful, you can see that there is changed, yes, there is changed B0 and B1, this is B1, the slope, and B0 is the last one, yes? So we have y is equal to minus 161.68 plus 7.58x, yes? So this is our regression line. So what else can we do? So we describe the dependence of cost on the price, yes, by the line. Assess the quality of the model by the coefficient of determination. Coefficient of determination, R squared. If you check your formulas, it's necessary to find this one, yes, R squared, coefficient of determination or index of determination. What's necessary for us? To use regression, sum of squares, nominator, yes, regression, sum of squares, this one, and in denominator you can find a total sum of squares, yes, so regression sum of squares and total sum of squares. There is our output, yes, where can we find sum of squares. For example, here in ANOVA table, yes, ANOVA table is table designed for decomposition of variance, yes, and what can you find here in ANOVA? Do you remember my example about ANOVA table where you could find these values? Yes, you remember. There is source of variability, yes. There you can find source of variability, yes. I will write here just the shortcut, source of variability, yes. Regression, residual and total, yes. And what we need for the calculation of R squared, yes, regression sum of squares and the total sum of squares. You can see this E. Mr. Hellman called this E error sum of squares, and in this table error is residual, yes. For your purposes, yes, Mr. Hellman used error, E, so R, E and T, like regression, error and total. But here in this table, you can find R and T, yes, but you know that residual is the same, is synonym to error, yes. Okay, source of variability, yes, so we know what is here. What is it? SS, sum of squares, yes. So here we have sum of squares, yes. So this value, what is it, this value? Regression sum of squares, yes. And there we have a total sum of squares, yes. And the other things you will see later, probably in week number 11, yes? But now we have sum of squares. So you are able to calculate R squared, yes? R squared. I will calculate R squared here, yes? For example, maybe I can a little bit zoom this sheet, yes? Okay, so R squared will be calculated here, and we know that R squared is a ratio of regression sum of squares. This is divided by total sum of squares, yes? Okay, and there is the result, yes? 0.9704. We know that R squared is from range 0 and 1. If this R squared is close to 1, the model explains a lot of variability, yes? This is our case, yes, because we have here the value very close to 1. So we explained 97% of variability of data, yes? If you scroll up, yes, you can scroll up in this output. You can find here summary output, and there is R square. Yes, there is calculated R square by Microsoft Excel. You can verify that we calculated the correct value of R squared. Yes, maybe good for you is this value multiple R. Multiple R is correlation coefficient. Yes, correlation coefficient is called here multiple R. So we already calculated correlation coefficient manually on the calculator. Yes, so you can use the data variable y and variable x, and you can calculate correlation coefficient manually. Yes, you can try if you are able to find this value. Yes, so that's all. This is correlation coefficient and R square, index of determination. What else? Determine what average increase of annual costs corresponds according to this model to increasing of price by 1 million Norwegian crowns. Yes, it's necessary to know in which units we have data. Yes, price is in millions. Yes, and costs are in thousands. Yes, so what average increase of the annual cost corresponds according to this model to increasing of price by 1 million. Price by 1 million. Okay, so 1 times slope B1. 1 times parameter of slope. Yes, and our slope is 7.58. Yes, 7.58. So this is our model. Variable y is in thousands. Yes, costs. We have here costs in thousands. Yes, costs in thousands, and price is in millions. Okay, so the result is the value of the slope of the regression line. So because we know that this is in thousands, this is in millions, 1 times this value, it will be 7.58 thousand. So 7,580 Norwegian crowns. Yes, so this is the result, and this is the response of C. Am I right? C, yes. Average increase of annual costs. Yes, 7,580. And finally, we will calculate the amount of the costs when the price of the house is 80 millions Norwegian crowns. So we will calculate here response D. What we need to use intercept plus 7.58 slope times 80 millions. Yes, and the result will be in thousands. So equal sign intercept plus slope times 80. Yes, and this is your expectation. Yes, this is your calculation, this is your vision. Yes, of annual costs in thousands Norwegian crowns. What is the result? 400 and 44 thousandths and something. So result is 444,869 Norwegian crowns. Yes. Okay. So this is response D. Yes, I will move it here because this is response D. Okay, so we solved everything. Yes, this is in thousands 444,869 Norwegian crowns. We will continue. It was analyzed the amount of yield, yes, independence on the amount of used fertilizer. The data set is written in the table below. So you can see you have here the data in 2 lines, yes. And for purposes of our analysis, you need to transpose, yes, these 2 lines to columns. I already did this for you, but you need to know how to transpose these values. I hope that you are able to do this. If you don't know, study anywhere, yes? How to transpose these values to columns, because only in columns you can use function regression in our analysis toolpack, yes? So this is prepared for our presentation, for our calculation here, but for example in the test you must know how to solve this, how to use it, yes? So everything must be in columns for calculation, yes? Almost every time. So we have here a variable amount of fertilizer in kilograms and amount of yield in cubic meters, yes? And amount of yield is our dependent variable, and amount of used fertilizer is independent explanatory variable. Yes? We will fit the data by quadratic regression function, regression parabola, and we will compare the results with regression line. Yes? How can we compare regression line and regression parabola? For example, using some appropriate index or coefficient, yes? So we will try this, yes? What we need for the quadratic regression function, regression parabola. We have variable y, variable x, and we need also variable x squared, second power of variable x. Yes, why? You can check your formulas. In your formulas, you can see quadratic regression function. Yes, y is equal to b0 plus b1x plus b2x squared. We don't have x squared here, so I will calculate here. Yes, I will calculate here x squared. Yes, here x squared. Wait a second. Okay, so equal sign. Yes. Variable x times variable x one more time, yes? This will be the second power, for example, yes? And now I have here 3 columns, y, x, and x squared, yes? So this is my data set. What now? I must find on the data leaf, yes, data leaf, data analysis toolpack here in the right top corner, yes, and I must find regression. So please use regression function, okay, and I will delete this, I will delete this, yes, and where I have my data set. Here, yes, there is my data set. So, input y range, yes, input y range is one column of variable y, yes, input x range, two columns of variable x and x squared, yes. Do you understand to this principle? Input y range, one column, input x range, two columns. We will use labels, and that's all, yes? So, do this, yes? I will select input y range, this column with labels, input x range, these two columns with labels, yes? Okay. And I will zoom this output. I will use stronger columns, yes. Okay, and I will delete what is not necessary. This is not necessary for us. I will use only 2 decimals, yes, because 2 decimals is enough for us, okay. Here also just 2 decimals, and here, for example, 4 decimals. Yes, so there is parabola. Parabola. I renamed this sheet. Yes. Okay. So where we have coefficients of regression parabola here. This is B0, yes. This is B1, and this is B2, yes. B0, B1, B2. Yes, you can compare this with your formulas. There is your function, yes. Y is equal to B0 plus B1x plus B2x2, yes. And we have 3 B's, yes. B0, B1, B2. So in our situation, in this output, yes, you can write, for example, here, wait a second, that variable y is equal to minus 32.22 plus 7.3x plus 0.72x squared. I will use right button, format cells, superscript, okay, and this is my equation, yes. What else was written here? Fit the data by quadratic regression function, parabola, and compare the results with regression line, yes. So I will calculate the regression line as well, yes, and after I will compare results, yes. So there is my data set and regression line using variable x and variable y only. Variable y and only x without x squared, yes, because it's only line, yes. So again, we will use data leaf, yes, data leaf, right top corner, and analysis toolpack. Toolpack analyzes data analysis, regression, okay. I will delete this, I will delete this, yes, and I will select input y range. Input y range is this column, yes. this column only. Input X range is this column X. This column only, yes? And that's all. I have selected labels. Okay? And you will see different output, yes? I will delete what's not necessary for us, yes? So please wait a second. This is not necessary, yeah? So I will delete this, and I will use only 2 decimals, yes? Only 2 decimals. Okay, and 4 decimals here. Perfect. So, coefficients, yes, this is the line, yes, this is line. This is parabola, and this is the line, yes, and according to this parabola, I can write a function for the regression line here, yes. You know that regression line using only B0 intercept and slope, yes. So minus 53.88 plus 15.40x, and that's all, yes. So I will write it here. Minus 53.88 plus 15.40x, yes. So this is the line, and this is parabola. But I must compare the line and the parabola. How? How can you compare 2 models? Parabola using 3 B's, 3 coefficients. Line using 2 coefficients. Mr. Hellman said to you that different models, which modeling the same in our situation amount of yield, yes, different models you can compare by adjusted R squared, adjusted version of coefficient of determination. Adjusted R square, yes, that's all. To be continued. We don't have enough time in this seminar, so remember everything, yes, what you could see today, and next week, yes, be prepared in this point. So make ready your example with amount of yield, observation variable amount of yield, and observation variable used fertilizer, yes, and we will continue with this adjusted R square, because it's very important for comparison 2 or more different models modeling the same thing, yes. So this is the end of our 5th seminar, yes, and next week I will see you again, and we will continue, yes, in this point. So it's very important to be ready, yes, in this point next week. So I hope that everything what you could see is alright, it's clear. Have a nice day, have a nice week, and I will see you next week. So thank you for your attention, and bye bye.